In this video, we're going to look at the idea of sum to infinity of a geometric series using Zeno's paradox. So Zeno's paradox says this: a man standing in a room cannot walk to a wall. In order to do so, he would first have to go half the distance, and then half of the remaining distance, and half is still what remains. And this process can always be continued and never can be ended. Therefore, he would never reach the wall. Then we know in reality that, of course, if he does walk towards the wall, he will actually eventually hit it. So let's see if we can look at this idea. This is known as Zeno's paradox. So consider a man standing 16 meters from a wall. So we've got this little animation here. So what we've got here is a wall. We've got a line here, which is, there's our man, and we know that this distance from here to the wall is 16 meters. So the man, first of all, works half the distance. So he's going to walk to this point here. This is going to be fun. Let's see. So he goes to this distance here, and therefore he's walked 8 meters. He still has to go halfway again. And now he has walked 4 meters. So altogether he's walked 12 meters. And then he still has to go halfway again. And he now walks 2 more meters. And then he still has to go halfway again. He walks 1 meter. And then he has to go again one more time. Well, not a lot more time, sorry, which is going to be a half meters. Okay, obviously the animation is going to sort of stop here. It's going to half again, which is going to be a quarter meter, a half again, which is going to be an 1/8 meter, and so on. So let's just have a look at this mathematically to begin with. Now, we can notice that 8, 4, 2, 1, and a half is a geometric sequence, in all terms of a geometric sequence, with a common ratio of a half, because half of 8 is 4, half of 4 is 2, etc. Half of a half will be a quarter, half a quarter will be 1/8. So let's have a look at this in a bit more detail. So the sequence 8, 4, 2, 1, a half, a quarter, and 1/8 is known as a geometric sequence. It has a first term of 8 and a common ratio of a half. We can get that by doing 4 divided by 8, that gives a half. 2 divided by 4 gives a half, etc. An 8 divided by a quarter will also give a half. Any term in this geometric sequence is given by the first term times the common ratio to the power of the term number minus 1. So in this case, that would be 8, which is the first term, times the common ratio, which is a half, to the power of n minus 1. Now, more interestingly, the sum is given by Sn is equal to the first term, brackets 1 minus the common ratio to the power of n, divided by 1 minus the common ratio. So in this case, that's going to be 8, first term, times 1 minus a half to the power of n over 1 minus a half. Now, 1 minus a half is a half. 8 divided by a half gives me 16. So this will come down to 16 times 1 minus 1/2 to the power of n. Now let's see what happens here. So if we go back to this animation, obviously if it carries on, okay, and then obviously it gets too difficult to actually animate it anymore, okay, but if we now look at this table, here we have the term numbers 1 to 20. This obviously can carry on more, there's a lot more than 20 terms. This is the actual term number. So the first time he travels 8, then he travels 4, then 2, and then 1, a half, a quarter, 1/8, 1/16, etc. This here is the sum of each of these terms. So this will be 8. Next one will be 12 because it's 8 plus 4. The next one will be 14 because it's 8 plus 4 plus 2. And then the next one will be 15. And then what we notice is actually as we go down here, the sum is approaching 16, which is what we would expect it to actually do, because the more times we actually do this, this will actually get closer and closer to 16, but will never actually reach 16, but it will be very, very small that we can probably just ignore the little gap. So it's better to see this looking at a graph. So here we have a graph of the term number against the sum. So it's this column against this column. If we click here, that here is when it is equal to 1, 2, 3, 4. And what we see is that it's actually approaching the line 16. Obviously, this is so small that we can't actually see the distance. So actually, what the sequence is actually, the sum of the sequence is actually doing is actually approaching a number, in this case 16, which is actually the actual length of the man, that the total distance that the man actually had to walk to hit the wall. So what we are saying is that the sum, and we use this word, converges on to 16. Okay, and not all geometric sequences will actually converge onto a number. We can look at when it will and when it won't in a minute. Okay, so just carrying on. So what happens to 1 over half to the power of n when n gets large? Well, just stop the video and try on your calculator. Do a half to the power of 20, a half to the power of 100, and you'll see that this number here will become very, very close to 0. So as n gets large, then 1 over half to the power of n, so n being like 20 or more, will approach the number 0. So if we look at that with our formula, which is 16 times 1 minus a half to the power of n, this bit will be equal to 0. We just say it's actually equal to 0, so that the sum of the geometric series will become 16, which is 16 meters, which is the actual length of the wall. And what we've taken is an infinite number of terms of this original geometric sequence to get 16. So this is the same distance as the original distance from the wall, which was 16 meters, if you remember. So if we now look at this with the general formula, now the condition for a geometric series to converge is that r must be between -1 and 1, i.e. a fraction. It could be negative or positive, but it must be between -1 and 1. And for all other values, except 0, it will in fact actually diverge. So you cannot actually use what's known as the sum to infinity. And as for large n, r to the n will approach 0. So that means that this bit here will become 0. So our sum and we now call it sum to infinity, will now become a times 1 minus 0 over 1 minus r. 1 times a will give me that the sum to infinity becomes the first term divided by 1 minus r. This is known as the sum to infinity, because what you've actually done, you've actually found the sum of an infinite number of terms. And so the man walking towards the wall is actually, he can walk there an infinite number of times, walking half the distance. So eventually he will actually walk 16 meters. And we know if we set a man off 16 meters from a wall and he walks towards it, he will actually eventually hit it unless he stops. Okay, so just one important thing to remember is note that the common ratio for this to happen must be between -1 and 1. So this has been a video to introduce what's known as the sum to infinity of a geometric series. We've used one of Zeno's paradox to sort of introduce it. I hope you've understood, and I thank you very much for watching.